everybody. So last class we talked about what happens when we do substitutions on a ring that have a substituent on it, and we found out that electron donating groups direct things to the ortho-para positions. And one of the things we went through, and we talked about the transition states of the intermediates and the stability of the intermediates involved and how electron donating groups stabilize that rhenium cation intermediate. And then we did this little thought experiment where we imagined that a very good donating group would be the CH2 minus, a negatively charged thing, and we take a look how we can distribute that charge around the ring, and we find that these are the most reactive sites on the ring in the ortho and para positions. We did the same type of thought experiment where we said, well, a CH2 plus group would be a very good electron withdrawing group, and through resonance we can delocalize the charge, and what we find out then is that these positions would be the least reactive in that type of cation. So that helps us to think about electron donating groups are ortho-para directors, and electron withdrawing groups are meta-directors. The ortho-para work because they activate the ortho-para position, and the meta-directors work because they actually deactivate the ortho-para positions, and it's the meta that remains slightly reactive. Then we took a look at chlorine, and we found out that chlorine is electron withdrawing and is still an ortho-para director. Okay, so what's going on here? And we talk about how halogens are inductively electron withdrawing, but they are through resonance electron donating. So in these cases we can draw similar resonance structures for the para isomer but not the meta, so we can see that we can stabilize these intermediates in the ortho and para direction. If we do the substitution in the ortho and para positions. And if we think about this in terms of the transition states, although chlorine is deactivating, in this case it deactivates the ortho and para less than it deactivates the pathway for the meta position in a similar fashion. And I wanted to just remind you folks a little bit about So classification of substituents for electrophilic aromatic substitution in terms of ortho-para directing or meta-directing. So electron donating groups are ortho-para directing always. The very weakly deactivating halogens are also ortho-para directors. The rest of our electron withdrawing groups become meta-directors, whether they're moderately or strongly deactivating. So one of the things you need to be able to do, especially we're going to talk a little bit today about what happens when we have disubstituted benzenes, and you can imagine that there may be a fight between the substituents as to where they're going to direct things. So you need to be able to assess the relative strengths of groups. And these are more or less in order, although this would actually be very strongly activating and should be up here, I suppose. And you could imagine if we removed a proton from here and we had an NH2 minus, that would be very strongly activating as well, because then we would have a negative charge. I didn't get them up. I just finished them this morning. I'll put them up. I'll warn you at the end of today's lecture, I haven't made the slides yet. I've still just ripped off, and I haven't made my own slides. But I will be fixing that as well. So I'll put these up after class, and then I'll put the modified ones up again. So we have these strongly activating groups. How can we make an assessment as to whether something is strongly electron donating or not? One of the things you want to think about is inductive versus resonance and the importance of pi donation. So here we see a cation, okay? And in this cation, the oxygen is more electronegative. I'm sorry, we don't have a cation here. We have, this is just methyl T-butyl ether, okay? And oxygen is more electronegative than carbon. We know that we can guess that because of the trends in the periodic table, and we look and oxygen is to the right of carbon, and they're in the same row. So oxygen is more electronegative. And in this methyl T-butyl ether, we would have a polar bond. And in fact, this bond would also be polar. But I'm showing here because I'm going to show what happens when we make the cation. But anyway, this would be a polar bond. This is a polar compound. It's actually significantly water soluble. I think it's around 26 grams per liter that you can get of methyl T-butyl ether into water. So it's a polar compound, and that's due to the electronegativity of the oxygen. If we make, so we think of as oxygen, it is electronegative, and we're used to seeing negative charges on it. But then we also know that if we make this cation, we see to the right here, this thing actually, we can draw a resonance structure. And we actually talk about this as being the best contributor to the overall structure of this particular cation because this one has an octet of electrons on all of them. This one does not have an octet of electrons on carbon. So we talk about, organic chemists anyway, will talk about this as being the best contributor to the real, true hybrid structure of this cation. So oxygen is, through resonance, electron donating. So oxygen has this split personality. It's electron withdrawing inductively, and that means through the bonds. It hogs the electrons in a covalent sigma bond. It's because of all the protons in its nucleus, a lot of positive charge there, and it's an electron hog in a covalent bond. But resonantly, through resonance, it's an electron donating group, okay? And with oxygen and nitrogen, which you'll see the most, it is this resonance dominates when it has an opportunity to be there. So when oxygen is next to a pi system, a bunch of p orbitals that it can delocalize the electrons in, its electron donating properties become more important than its electronegativity in terms of the strength of its donation. That's true for any p donors in the second row. We can imagine, and I didn't, so now let's do a similar analysis with chlorine. Here we see that chlorine is also more electronegative than carbon. This would be a polar bond, just like oxygen. Now we can also make a similar cation. As it turns out, this is somewhat water soluble, but one of the problems with it, it's a gas, so it's not real water soluble. But we can draw this carbocation. And we can draw a resonance contributor where we donate the electrons from that p orbital into the empty p orbital on the carbocation and make a pi system. But as it turns out, when you do calculations and you do measurements for this particular cation, this is actually a better resonance contributor than the one on the right, which doesn't make sense when we did that last analysis of with the oxygen. With the oxygen, we said this was the better contributor. So what's going on here now? What's going on, and why is this the case? We have to go back to first year when we learned about atomic orbitals. And this is an s orbital, but it's a 1s orbital. 2s orbitals actually have a node. Remember we talk about the s orbitals being onion-like when we get to the 3s and the 4s? There's this change in phase within the s orbitals. The same is true for p orbitals. Here's a 2p orbital, and here's a 3p orbital. And now when we see, when we put the phase in there, what we see is we have these changes in phases in a 3p orbital. So when we try to make a pi system, as long as we have 2p orbital overlap, we get very good overlap, and we get very good bonding in our bonding interaction. And then we have anti-bonding, but that doesn't matter because we don't put electrons there. So with 2p overlap, we get very good overlap, much more stable molecular orbital. We get quite a bit of stabilization. But with 3p orbital, what you can see is this is positive orbital overlap, but as it goes more, there's destructive overlap here. So 3p, 2p pi bonds are not very stabilizing. They're only moderately stabilizing. Once you start pushing those atoms closer and closer together, you start getting destructive interference between this part of this p orbital and the other lobe. So 3p, 2p overlap is not really as stabilizing as 2p, 2p overlap for forming pi systems. So that's why these cations, we talk about that being a better contributor than the one on the right because of that. Now, as it turns out, this is a very unstable carbocation because of that, because you don't get as much pi stabilization or pi donation to that empty p orbital. So you should go through these substituents and see if you can justify their position in this table. What you will notice is the most activating are when we have a lone pair of electrons that are bonded to the pi system, because now the electrons in this p orbital can take part in the pi system and donate their electrons to that. If we put something like an acyl group on the nitrogen, now that lone pair of electrons, although it can still be shared this way, it can now be shared into this pi system as well. And we have the electronegative oxygen that really sucks up that electron density. So this is less of an electron donor as soon as because we've kind of deactivated it by putting an electron withdrawing group on the other side of it. So we have very strongly donating. These are less strongly donating. Now these, the weakly activating, do not have lone pairs of electrons. So they're relying only on their inductive electron donating abilities. Then we get down to the deactivating. With the meta-directors, what you'll find is this is mostly, there's a pi system there that accepts electrons. We have electronegative atom at the end of that pi system. So these are good at sucking electron density out. But notice now that it is the carbonyl carbon, okay, the sp2 carbon that's bonded directly to our pi system. That's a requirement. When we have this oxygen over here, this becomes an electron donor, but when it's the carbonyl carbon bonded, it becomes an electron withdrawer. Then we have some strongly deactivating groups. You can draw a resonance structure. The NO2, we have a positive charge in one of the resonance structures. We can have ammonium types of cations, right? There's a full positive charge there. That's going to be electron withdrawing inductively because of that positive charge. And then the CF3 and the CCl3, we've just put a lot of electronegative atoms on the system, and that withdraws electron density. So you want to kind of, you can memorize this table as well, but you want to have some idea as to the strongest electron donors and the strongest electron withdrawing groups. And now here's a reaction. So we've talked about the fact that this is, is this an ortho para-director or a meta-director? We have nitrogen with a lone pair of electrons on it. You could bond into that system. So we talk about this as being an ortho para-director. Okay, so what might we expect for these products as we find out why is it going to the meta position? Can anybody think? What's that? There might be steric reasons, but there's something else. What kind of conditions are we under? Very strongly acidic conditions, right? This thing is a pretty good base. So that's not the reactive nucleophile. As it turns out, we protonate that, okay? So under these strong conditions, there would actually be almost no unprotonated aniline around. As it turns out, there is some unprotonated aniline. The unprotonated aniline reacts much faster than the protonated aniline with our electrophile, and we do get a significant amount of product in the ortho and para positions. Just so happens under these conditions, this becomes the major product. So what I'm telling you is you got to be a little careful. You can't forget about the conditions as well. I'm not going to be trying to trick you with these things, but I may give you a question like this and ask you to explain why we would get a significant amount of the meta product here. Okay, and in fact, it's interesting that if we do this particular reaction, we're going to start talking about disubstituted benzenes in a second. And when you have disubstituted benzenes, both of these are ortho pair directors. So this is directing to this position and this position, and this one is directing to this position and this position, which one is going to win. In this case, we can actually switch it out. If we do this reaction under highly acidic conditions, this is, for the most part, all of them are protonated under these conditions, and you wouldn't have any of the unprotonated form. And this is the major product because that is directing meta once it's protonated, and this is directing ortho-para, so that becomes the position. If we do this in a slightly less acidic, it seems odd, but glacial acetic acid can be used as a solvent. This is a considerably less acidic system than this is. The nitration will still occur. There will be a significant amount of this that is not in its protonated form, and that one reacts very much faster. So even though it would be the minor, most of this would be protonated. Any of the unprotonated form reacts thousands of times faster than the protonated form. So it can compete with the electrophiles, and our major product now becomes in the other position. So we've switched it by changing the acidity of the environment. Even though this is not a friendly environment, you wouldn't want to fall in a vat of nitric acid with glacial acetic acid. It's pretty acidic, but it's not as acidic as sulfuric acid. Remember, sulfuric acid is a strong acid. Acetic acid is a weak acid. Most of it would be in its protonated form, most of the acetic acid. Most of the acetic acid doesn't give up its proton. So now we want to talk about what happens when we have these disubstituted benzenes. So you can imagine if we have positions where they're fighting each other here, right? This one is directing to these positions, and this one is the same, but it's to the other. But it doesn't matter. This is symmetric. What ends up happening is at least if we just do one substitution, these positions are equivalent. We can have reinforcing where this is an ortho-para director, and the para position is blocked because there's no proton there. And this is a meta director, so they're both pushing the substitution to go to the same position, and that's what you get. Where it becomes problematic is when these things are antagonistic, when they're going to the different place. In these instances, typically the activating compound wins. Okay? In this case, this is more activating than this because of the lone pair of electrons. We're not under extremely acidic conditions. This is going to remain unprotonated. That's going to be more strongly activating than this, and we do get our substitution ortho to the strongest activator. And in this case, now, even though this might be slightly better activator, someone said sterics a little while ago, sterics can sometimes dominate in disubstituted reactions in particular. So this position just becomes a little bit crowded, and we get more nitration in this less crowded position. So let's take a look at what happens when we have disubstituted benzenes. So in these four instances, they're all cooperative. So these are both oro-para directors, so they're that's ortho to that position, that's ortho to that position, that's also ortho. None of them are directing to this position, so we don't expect to see any substitution in that position. In this one, they're both directing to these positions. Here, this is directing to this position and this one is also directing to this position. And here, they're both meta directors, so they're both pointing to that position. So what happens? We can imagine that some of these positions are more reactive than others, and that turns out to be the case. These positions accept one new substituent. A second is possible, but forcing conditions may be required. And that's mostly, we can typically put one either here or here. We're really bulking up the molecule. Putting that fourth substituent on is typically not very easy. But for all of these positions, they quite readily get substituted. The next one are amber light. This one is the position of choice. I'm sorry, it's not the position of choice. This one is less reactive than this position, and mostly just because of the steric hindrance. This one is the only choice for substitution to go to, but the reason we have an amber light there, can anybody tell me? Why might we have an amber light there instead of the green light in the other positions?
Is it because the meta groups are only directing in that they like deactivate?
It's the deactivation. Both of these would be deactivating groups, and so this is just not going to be a particularly good nucleophile, and we usually have to use harsh conditions. These ones go quite readily because we have two activating groups, so this one goes fairly readily. And these ones, it's going to depend on how much activating one group is and how deactivating the other. So this one, these reactions will go very rapidly. These ones we'd have to do an assessment. These ones are likely going to go slow, but we do have a nice wide open position that we can get to. And then we have a couple of what we call red light positions, okay? The meta position, substitution just doesn't occur there to an appreciable extent between two meta groups. Even though this one is both directing them there, it's quite sterically crowded, and there's easier places for the substituents to go. This one, it's sterically crowded, and nothing is directing anything there. So that's a definite red light. So it becomes, so there we can take a look at the slide and the complete analysis, and maybe take a look and make sure that you're happy with those arrows and you can explain them. This is just showing a few reactions. So here, obviously, both of these are directing to this position, and this position is not going to matter because of the symmetry of the molecule. Once we do one, and this reaction actually would do one monosubstitution because we're deactivating the ring by putting an electron withdrawing group, so we probably could do a monosubstitution. This one, they're both, again, because of the symmetry, they're going to go to either one of this position or this position. It's going to be the same. These ones, they're both electron withdrawing. They're both going to point to the meta position, and we get the meta position. And up here, again, we have a ortho-para director and a meta director, so we're going to do the sulfonation in that position. This position, perhaps, but it's a little bit more sterically crowded just because we have some groups there. So usually it's hard to get three in a row. If we can, we'll go to this other position. Same thing now with this one. This group, ortho-para directing. The pair is blocked, so it's directing to these groups. This is meta-directing, also directing to here, and that's what we end up getting. We can actually do, in this case, this is strongly enough activating. This reaction goes quite fastly, and we can get substitution in both positions. And finally, same with this one. This is a good activator. We try and make sure that our conditions are such that we don't have acid around, and we can direct them there. With disubstituted benzenes, you're going to have a little bit more of an analysis to do. Typically, when two different groups are present, the more powerful resonance donating group generally determines the outcome of the product. So the resonance donating group dominates, okay? And that's because it's going to be activating through resonance to those positions ortho and para to it. So it's more activating than the other one is deactivating, typically. All of these ones are directing groups that are fighting each other. If there's not a resonance donating group, then the more activating or less deactivating group will be more influential in product determination. Okay, so typically the group that is activating will determine the product distribution. Steric effects can be more important than small differences in directing effects. So steric effects become pretty important when we have these antagonistic substituents. Here's a bunch of examples. Now, this example we've seen already, right, where we can switch, and a lot of that has to do with the acidity of the environment. Same thing with this one. Actually, we end up going here because of the stronger donating group. We have to be careful with our acid. If we have a lot, if we're under really strong conditions, that's going to become protonated, and we may end up making that a meta-director if we have too acidic an environment around. Although this is not nearly as basic as the aniline counterpart. If that were a nitrogen, that's a stronger base. Down here, we end up, even though this might be a better director. It's also more sterically hindered, so we end up going to the less steric position. And typically what you're going to see when you have big groups here, if you have to make a decision, it's probably going to go to the least sterically hindered. This one doesn't matter, even though they're fighting each other because of the symmetry. The groups end up being the same. And in this one, where do we go? We end up going, in this one, it might be hard to predict. This is a better resonance donator than this one, even though this one is slightly deactivating through resonance. So these ones actually are the ones that I would just not ask you questions about these because it's really hard to tell. Okay, so I'm not going to be asking questions about very subtle differences. The last part of this chapter has to do with the reactions of alkyl benzene side chains. So we have our aromatic group, but we can't forget that we have stuff outside of here where chemistry may happen as well. Toluene we already know about, ethyl benzene, isopropyl benzene, typically we'll call this cumene. And then this compound styrene, most of you are familiar with styrofoam. It's made through a polymerization reaction. These things have slightly different chemistries than we might expect because of the aromatic group to which they're attached. So we can imagine the benzyl cation is very much like the allyl cation. We can delocalize this positive charge throughout the pi system. So benzyl cations and benzyl radicals are much more stable than we might otherwise expect. Exactly analogous to the allyl system. It's because we can delocalize that charge or we can delocalize that spin. Okay, so the benzyl cation, very similar to the allyl cation in that the charge can be delocalized and it's much more stable than we might otherwise expect. So the benzyl position is very susceptible to radical reactions because the benzylic radical itself is very stable. We can take toluene and we can put chlorine in there. We have to use quite a bit of heat or an initiator or light to start forming some free radicals, and then it will undergo this radical type of reaction. I didn't get this slide made, but we can do it on the board. What we expect, so if, remember, benzylic hydrogens are easily abstracted by radicals. So all we have to do is make some radicals to make this reaction happen. So these are free radical chain reactions. And the way they work, we need something to initiate the reactions, and that is where we form radicals. We may do something like zap chlorine with light, and when we do, it breaks this bond in a homolytic fashion. Oops. And we get two chlorine radicals. Don't forget the other lone pairs of electrons on there, but the chemistry of this is dominated by that single electron that makes it a free radical. It's just atomic chlorine is a free radical. Another initiation reaction that we can do, we typically take something like this. This is benzoyl peroxide, and we just heat it up. Oops. Heat it up. That's a very weak oxygen-oxygen bond, and we end up getting two of these radicals. Okay? So we get radicals in our initiation step. The next step we talk about is the propagation steps. Okay, so our propagation steps, some radical will come along. If we made, I'm going to do this. We abstract a hydrogen, and we abstract it homolytically, right? So one electron pairs up with this electron to form an HCl bond, and it pulls off this, and we get this radical plus HCl as our product, okay? We have to have another step, and our other step then involves this thing reacting with makes a free radical and our other product. So these are products. I'm going to say stable products. So notice what happens is this is a chlorine radical, and it abstracts a hydrogen atom to form the phenyl radical, I'm sorry, the benzyl radical. The benzyl radical goes on to react with chlorine and produce this thing. Notice that this thing can just go back up here, and this one goes here. That's a little confusing, but one of the products of this reaction is a reactant in this reaction, and one of the products of this reaction is a reactant in this reaction. So all we have to do is get this reaction started, and it zips along. This is the chain. This reaction will just keep going. What stops the reaction? Termination reactions. So either any two radicals coming together okay, as well as all of these stop the reaction. They terminate it. Because once we form the free radicals, they get in this chain. This chain is going to keep going, but these termination reactions pull the reactions out of the chain and stop the reaction. So every time, if we just make two radicals, we can get two chains going, but then if two radicals come together, that chain will stop. Okay? So take a look at that. I'll get the slide made up as well. Alkyl benzenes, okay, these are both alkyl benzenes. If they're conjugated with the ring system, they're much more stable. We expect that because now our pi system is conjugated. Those electrons can delocalize. These ones cannot. So this is just like when we had the allyl systems. We have an sp3 hybridized carbon here that keeps these two pi systems from communicating. Here we have a complete sp2 system so that they can communicate. So this typically is a more stable outcome. And we see that for this type of reaction. We can imagine what's going on here. You guys, this is, what kind of reaction is this? Do you remember? This would have been from last semester. Alcohols react under acidic conditions. We protonate there. Water pops off, and we end up getting a carbocation. Oh, I don't have the mechanism yet. So, but we're going to have a carbocation center there. Let's draw the carbocation that we would have. and we can remove this proton. We actually have 2 protons, right? And if we have, there we go, some water molecule around, because we protonated that, popped off, water molecule can go around. If it pulls off this proton, we end up getting this reaction. And if we pulled off this proton, we would get and this does not form. Because of that sp3 hybridized carbon. So this is kind of thermodynamically controlled. The stability of the product dictates which one of those protons. The protons, these protons are much more acidic, we might say, than these protons, because this proton will be removed. These protons will not. We get none of that product because of that conjugation. So you need to look at what are the intermediates for those addition. Oh, I have my slides mixed up. We can do addition reactions. So here we have a styrenyl type of compound. Our double bond is conjugated with the ring. If we react this with HBr under conditions where we add a free radical initiator, we get this product. Notice where our bromine goes to this position. If we do the reaction with no peroxides, a little bit of heat, we get a different reaction. We get substitution here, okay? So what is going on? What kind of reaction? We talk about it being an addition reaction, but we're actually going to protonate this in this case. Which cation is going to form? Is it always the most stable or the least stable cation that forms? Always the most stable cation. So this goes through cations. This goes through radicals, and we're going to end up adding a radical to the double bonded system. So under conditions where we have a peroxide around, we make free radicals. We have lots of HBr around. We're going to abstract that. We're going to form our bromine atom. Our bromine atom just adds to the pi system to form the most stable radical. This is more stable. It will form. That then can start this chain reaction where it will remove a hydrogen atom from hydrogen bromide, producing this product, as well as a bromine atom, which just goes back into the chain. Okay? So this is a free radical chain reaction, and it goes this way because of the stability of the benzyl radical. This is not a benzyl radical. It's a secondary radical, and it's much less stable than the benzylic radical. So this addition does not occur when we get the addition of the atomic bromine. It only goes in this position. On the other hand, for this reaction, we just pull off a proton from our acid, and we form carbocation and the bromide. This carbocation is much more stable than this carbocation, and all of the chemistry comes from this carbocation, and that's why we get the substitution there. So we have an easy way of putting our bromine either in the benzylic position or in the position next to the benzylic position, way back here. Okay, we can make either one of those simply by changing conditions, and it's dominated by the stability of the intermediates. As it turns out, benzylic positions are quite easily oxidized with KMnO4, and they go completely to the benzoic acid. All we really need is something to work with in that benzyl position, and we can make benzoic acids. All of these compounds will get oxidized. All of these are supposed to be heat, by the way. We need to use fairly harsh conditions, but we do the oxidation, then we work it up with acid, and we get benzoic acids. As long as we have either a benzylic hydrogen or an sp2 hybridized carbon there, or sp3. We need either benzylic hydrogen or pi system, and we can do these oxidations. If we block that system completely by putting, there's no benzylic hydrogen and it's sp3 hybridized, this reaction doesn't occur, okay? But we don't need a lot. All we need is a little bit of a handle to get that oxidation to occur. The last thing I want you to take a look at is this substitution reactions. Just take a look. Benzylic positions typically can undergo SN1 or SN2 mechanisms, and it's going to depend a lot on the conditions, so we're not going to go there. Usually, if you're doing a new reaction, you'll try it. If you get the product you want, fine. If not, you may have to work if you need to get it to go through one or the other mechanisms. If we have disubstitution on our benzyl position, these will go through SN1 reactions exclusively. So we're pretty well done with this chapter. We're not pretty well done. We are done. Here's the concept map. This looks confusing. It's actually not that bad. This is just telling us when we have an aromatic ring, we can activate it or deactivate it towards electrophilic substitution. This is what we've talked about in this. This is basically a summary of what we've done, the slides we've done. Here's the reaction concept map. Again, it looks a lot more confusing. We've covered almost all of these reactions in the classroom. We didn't really get into this, but we did discuss it. We did not look at this reaction. I think that's the only one that we didn't look at. Now, since we have a few minutes and people have been asking for some problems, there's some problems on the ends of this slide, okay? Oh, by the way, should get an email. I'm trying to get BAC 244 for tutorials starting tomorrow night. The way the tutorials are going to work is I want you guys to work on problems, come, and I'm not bringing any prepared material. It's to work on problems either from the assignment, or I'm going to start putting some problems out there for you to work on. I'll probably just put them in PowerPoint slides. Okay, so how would we make this particular reaction? How is this going to work? How would you start it? So you want to put two substituents on it, and they're in the para position. Kind of dictates what you have to do, doesn't it? It tells you that you're going to have to put the ortho-para directing group on first, and then the next group. So this one is fairly easy. You would just have to do the Friedel-Crafts acylation, although it's kind of hard because it goes, you actually end up getting multi-substituted products, but you can sometimes purify them. Here's another problem. How would you go about doing this one? This is an interesting problem because your textbook, or the notes from your textbook, actually came up with a synthesis. Okay? So this is from the notes in your textbooks. They said, well, why don't we just nitrate this compound? Now we have a meta-director, and we can do the Friedel-Crafts alkylation reaction, and then we can oxidize the benzylic position and get our compound. Anybody see anything wrong with this? The alkyl group is an ortho-para director, but we... No, the NO2 group is a meta-director, very electron withdrawing. This is one of the limitations of the Friedel-Crafts reactions. Remember we had all those limitations? One of them was it really doesn't work well when we put deactivating groups on the ring. So this reaction, if it went, it would be a very poor yield. Okay, because these reactions don't work when we have electron withdrawing groups on the ring. They either don't work or they don't work very well. That's one of the limitations of the Friedel-Crafts reactions. Okay, so I know when you go through the slides you'll remember that better. So this wasn't actually a particularly good way to do it. What I would have done was put this group on first, but differently. How might we do it? What if nitration reactions go very not very well, but we can force nitration reactions even when we have electron withdrawing groups on the ring. So we might think about making this a formal group, and then it would be a meta-director, or, oh, no, it's even easier than that. Let's put it we want to be careful with this reaction that we don't over-alkylate, but we can do that by doing it under dilute conditions, and we make this compound, okay? Then we just oxidize it. And we get this thing. What kind of director do you think that's going to be? Meta-director or ortho-para-director? So this would be a better method. In this reaction, this is going to be a very low yield reaction if it goes at all. And these are all high yield reactions. This is a high yield reaction. This is a high yield reaction. And this is a decent yield reaction as well. Nitration reactions typically go in good yields. Sometimes we have to force them, like to make trinitrotoluene. Putting that last nitro group, we really have to force it. But they go in pretty high yields. So there is a better route. Oh, there we go. I did put it there. Okay. So that's a better route, goes in higher yields. How would we do this? Here's some problems. Since we're almost, we only have 3 minutes. This is an interesting problem, but I'll tell you, this one seems like an easy problem. Why don't we just, our amino group should be a ortho-para-director. Why don't we just go ahead and do the bromination? Well, what turns out to happen here is that our para is only once amongst many products. We get a decent yield, but we get a whole bunch of products. And not only that, although you guys don't know, but trying to separate things with amine groups on them are kind of a pain. There's different ways to do it, but it is a pain. This would not be the major product. It might be the major product, but you would have significant amounts of these other products around. So there is a way to do this reaction. And here's a similar problem. If we wanted to do this nitration, we would have trouble avoiding getting the isomers as well as multinitrations, and there is a way to go ahead and do this using some of the chemistry. Now these two problems, so maybe we'll take a look at those tomorrow evening. You guys should give them an attempt, figure out why they're problematic. These I would consider very, on the difficult side, these two problems. This one is not that difficult, although it involves a little bit of, not trickery, but we have to be aware of what we're doing because they're both ortho-para-directors, so we have to do something to get them in the meta position. Oh, there we're done.